In this video, we are going to talk about really interesting stuff. It's about power delivery. And for example, what we will learn is how important it can be, how you do connections for decoupling capacitors. That's, for example, what we see here. There are different kind of connection, different via placement, and you can see actually it makes difference in power delivery. But we would like to start maybe with something more simple, something why this power delivery is important and how we can measure it with cheap and maybe even free software, cheap devices, so anyone can actually measure this. And Adinath is going to help us to understand first why this is important and then how it is going to help us. Correct, Adinath?
Yes.
Okay, so let's jump to one of your first slides and let's talk a little bit about this PDN, because I think this PDN is like very popular topic right now. So what does it mean, PDN, and why it is important to talk about this, and maybe also why we would like to measure PDN on our board?
Okay, thanks, Robert. So just to give you a background on why we need to do this low impedance measurements. So if we have a die, we want the voltage across the pads of the die to be constant. One thing that we can do is use a really stable VRM. However, due to the microcore that we may run, the transient currents through the chip may be sometimes really high, sometimes we won't have any current through the chip. So what happens is when the transient current, it goes through the impedance of the PDN, we get a voltage drop across it. And this induces the voltage noise. So in order to reduce the voltage noise that we have on the pads of the die, what we can do is we can reduce and keep the impedance of this PDN below a target impedance. And throughout, it should be throughout the frequency operating range of the device.
What do we see on this graph?
So in this graph, it's a normal schematic or equivalent circuit of how we have a VRM, and then this the part till the pads of the die, we have some impedance. We have categorized that impedance as the impedance of the power delivery network or the power distribution network, as we say that, and how a current going through it, and it has a particular impedance which varies with frequency, how it is going to induce a voltage noise and a voltage drop, which will be a voltage noise on the pads of the die. So this shows that, and this graph here shows the one in the red. The plot in the red shows the impedance of the system or the device plotted against the frequency, and then we see that the impedance varies with frequency. But what our goal is going to be is to keep the impedance over the entire frequency range below the target impedance that the manufacturers or the R&D engineers select for the device.
So this means basically we still will have some kind of voltage drop on this ZPDN.
Yes.
But it's going to be constant. So if we need, we can, for example, increase voltage a little bit or something.
The voltage drop is not going to be constant, but it needs to be below a certain level. So for example, plus or minus 5% tolerance level.
Yeah, okay.
If that's the case, we need to have the impedance Z such that it can be anywhere, but it should be below this target impedance line.
Okay. I would like to talk a little bit about this ZPDN. What people should understand behind this, like physically, not theoretically. So physically, what this ZPDN is.
So the impedance of the PDN will be the impedance of everything that comes from that comes in between the VRM and the pads of the die. So it is basically all the bulk capacitors, the ceramic capacitors that we have, the PCB planes and vias, the bulk vias, the package capacitors, everything that's in the way from the VRM to the pads of the die. So all of them have an impedance, and this cumulative impedance that the chip is going to see when it looks at the VRM is called the impedance of the PDN.
So I think what we should point out, especially for people who are starting with electronics, the kind of direct connection between power supply and chip, it's not really like direct connection. It's much more complicated. And even if they use DVM and measure resistance is 0.01 ohm, that may be true for DC currents, but for AC currents which are needed for example, processors which are switching at different frequencies, this is not going to be true. It's going to be full of capacitors, inductors, and these
Yes, yes,
components, they can manipulate
yes,
signals. And that's why it's important to measure this PDN profile, because we can see how the power delivery will be how the power will be delivered for specific frequencies. Because for some frequencies it may be a little bit easier to deliver power, for other frequencies it may be very difficult, like there will be high
yes,
impedance.
yes, exactly. Yes, exactly. And that's the need for measuring these low impedances. So to be able to analyze these PDNs, or able to be able to design these PDNs, we should be first be able to analyze and measure the low impedances of these individual components that we have, like maybe a resistor or a capacitor. And these target impedances of the PDN components are usually in the milliohm range. And this gives us the need, or this is the part where we have to use some technique to measure these low impedances. And today we are going to do that with a really low cost $450 VNA, so that each one of us, all of our audience, everyone can measure these impedances in maybe their startups, their college laboratories, anywhere.
$50? You
And
say
so
$50?
$450.
$450, okay.
Yes.
$450.
Yes. So, and using the VNA, we have two techniques that we can use. One is the one port technique, and the other is the two port technique. So the one port technique is not really practical for impedances that are lower than 0.1 ohms because of its real world limitations, like signal to noise ratio, or its fixturing reproducibility. So the method that we are going to focus on in this video is the two port method that we are going to use.
Okay, and basically with this special device, what we can do, we can actually measure the path between the power supply and the chip. We can measure the impedance or properties of this path. And what is special about this, basically we are measuring very low impedances. That's why we need this
Yes.
kind of special device.
Yes.
Okay, and a little bit later you will explain what kind of device we are using, so anyone can
Yes.
buy it, yeah?
Yes, definitely, definitely. So just to repeat what we just discussed, the measurement of the impedance of the entire PDN is a different study in all. But to be able to do that, first we need to be able to measure the impedances of these individual components, and that's what we are going to look out for today. And obviously with this low cost SDR VNA, and with a free tool which is Qucs.
But theoretically, once we learn how to do this for, I don't know, resistor or capacitor, you can measure it also on your own PCB, same way.
Yes, definitely we can, but to be able to measure it is one thing, and to be able to analyze it is another different thing. So I'll just measure it, but whatever data that I am seeing as the measured data, I should also be able to analyze the signatures. And to do that, there's a lot of background work, there's a lot of reading that one needs to do.
Okay, and basically that's why we are going to start with simple components, so
Yes,
we can
exactly.
understand these simple components first, and then once you make more complex measurements, you will understand better what is actually happening and what is measured. Okay,
Yes.
so let's do these simple measurements.
Yes. So before we actually begin with the measurements, what we need to do is we should, because this two-port technique using this SDR VNA is a new technique for us, and to be able to establish confidence in this technique, we should measure something that we already know the answer for.
Okay.
So we are going to start with measuring something as simple as a SMT, a surface mounted resistor.
Okay.
And before we actually do that, before we measure the impedance of this resistor across a frequency sweep, we should be able to, we should know what to expect as an answer to that measurement. So to do that, this is what Professor Bogatin says all the time.
Yeah, rule
So
number
to
9.
do that, yes. So we should know what to expect as an answer to that. So I tried measuring the DC resistance of some resistors that I had. So I had three resistors, 1 ohms, 0.5 ohms, and 0.1 ohms, and I measured the DC resistance of these resistors using the 4-point Kelvin method. So in this 4-point Kelvin method, what we do is we pass a known current through the device under test, and we measure the unknown voltage across it, and through that we calculate the DC resistance. And why did I use the 4-point Kelvin method? Because in this method we can get rid of the contact resistances.
Yeah, we made video with Eric about this, so if someone is interested to learn actually more details about this, they can watch this video.
Okay, so perfect. So these resistors were rated at 1% tolerance, and the resistance values that I got as a result of this 4-point Kelvin method measurement, you can see that they are well within 1% of the tolerance values. So now we know what to expect as an answer to the measurement when we actually measure these resistors using the 2-port method. So now we can go ahead and I'll introduce you to the device setup. I'll show you how to calibrate the SDR VNA. So this is going to be our SDR VNA that you see in the picture here. And we are shortly going to take an actual live measurement. But before we do that, let us first discuss what is the 1-port measurement technique and what is the 2-port measurement technique. So in the 1-port measurement method, what we do is we use just 1 port of the VNA, and we connect it through the transmission line to the device under test. And we have a 50 ohm transmission line, and then when it encounters an impedance mismatch with the device under test, because this device is going to have a really low impedance, we get a reflection. And we use this reflection coefficient, that is the S11, to get or calculate the impedance of this device under test. But in this method has some artifacts that get induced due to the inductive loop that we have. And so this method is really not practical to measure impedances that are less than 0.1 ohms. So for such low impedances, we'll move on to the 2-port method. So in the 2-port method, what we essentially do is we use both the ports of the VNA, and this method is fairly similar to the 4-point Kelvin method that we use to calculate the DC resistance. But this method is extrapolated in the AC domain. So this SDR VNA takes a frequency sweep from 1 kilohertz to 1.3 gigahertz. So what we are going to do is we are going to have this test structure that I'll show you shortly. And in that test structure, we have this device under test. So we use port 1 of the VNA to drive a current through the device under test, and we measure the voltage across it, which comes out as the insertion loss or the transmission coefficient. We
and the
then
current
use
is with different current of different frequencies.
Yes. So for each frequency, it will be calculating the impedance of the device, and that's how we'll plot it over the frequency range. And the frequency range here is going to be 1 kilohertz to 1.3 gigahertz. So we use port 1 to drive the current, and we use port 2 to measure the voltage across it. And this transmission coefficient or insertion loss, we are going to use that to calculate the impedance of the device for all the frequencies, and then we are going to plot it. So we are going to use this simple formula for that.
Cool. Okay. So for
now,
resistor is going to be flat, yeah? No, I'm not. It's not going to. I know.
We'll look at it when we come to that. So yes. So moving ahead, I'll like to show you our setup and the test structures that we are going to use, and how we use the simple low-cost calibration kit to calibrate the VNA.
Okay. So before we actually start, we have to calibrate it.
Yes, we do. So can you see my test setup here?
Yeah.
So this is our test setup that we see here. This is the SDR VNA that we were talking about. It measures a frequency sweep from 1 kilohertz to 1.3 gigahertz. This is the calibration, low-cost calibration kit that we are going to use to calibrate the VNA. So this consists of a through. This is a through. This is a 50 ohm test structure. This is a open, and this is a short. So we're going to use this SOLT low-cost kit for calibrating the VNA. And to do that, we connect the VNA to this application called VNWA. And this is how the interface is going to look. So just to get you through the process of connecting the VNA in brief. So what we do first is, so we go to options and then go to setup. In the setup, we will get an activation code with each of these VNAs, and we can type it here and then press the rescan and test USB interface, which will connect the VNA with this application. Once we do that, we are ready for calibration. And to do that, we go to settings. Before we actually calibrate, we'll select the type of the frequency sweeps that we want to take, because once we do all the settings, then we have to calibrate. If we change any of the settings after we do the calibration, we'll have to do the calibration again with the new set of settings. So first we select the frequency range. So we want to take a log frequency. So in settings frequency, we go to we select the logarithmic sweep. Then we go to the actual sweep settings, click on that, and we get this window here. So we're going to take 1,000 data points in our measurement, and the time per sweep, we are going to keep it to 30, because that's the maximum time this SDR VNA can have to take the sweep. When we are done with this, we go to measure, and then we can actually calibrate this VNA. So this window will appear when you want to calibrate the VNA, and these are the different calibrations that we'll have to go through. All the calibrations that you see now, it's already calibrated, and you see everything in green. To invalidate all those calibrations, I'll have to click on invalidate, and I'll have to click uncheck this box. And once I do that, I'll have to calibrate this again. And so I'll click on short, and then I actually use the short in this case, and I use it and I plug it using the barrel here. So just to show you, so I plug it using the barrel.
It's not visible on camera.
Oh, I'm sorry.
Yeah.
Yes. So I'll plug the barrel first, and then this is a short cal kit.
So you are putting this on the output?
I'm putting this on port 1 of the VNA.
Port 1, because I think it was marked like output, but it's port 1, yeah?
Yeah, yes, that's exactly. So this is the output. So we get the signal from here, and this is the input. So it will go into here. So this is port 1, this is port 2. And then I just press on short, and it will calibrate the short. Similarly, I do the open. So I take this off and I do the open. For the load, I use this, instead of the short, I use the 50 ohm termination in here. And then for the crosstalk cal, I leave both the ends open. For through cal and through match cal, I connect both the ends of the VNA through this barrel that we have. So I connect both these ends. Yeah. Okay. And I take the through match cal. And once I'm done with everything, this will show me all in green, and then I can exit out of this window. Just as a consistency check, we should check if we see cal written over here. And if it says cal, it means that our VNA is calibrated.
And so basically, once it is calibrated correctly, for example, if we use, I don't know, the 50 ohm termination or anything else, then we should see the specific results, like 50 ohm, around 50 ohm results, for example, or something.
Exactly. Like so that's the next step that we will do here. So now my VNA is calibrated, and to do a consistency check as to whether it's actually calibrated or no, I'll plot the open, short, and 50 ohm load, and I'll extract the data, and I'll plot it in Qucs. So this is the data that I've plotted in Qucs. And I'll shortly show you how to do that when we take our first measurement.
Okay, I'm curious.
So, yes. So the open, we expect the open to have a a reflection coefficient of 1, and a short to have reflection coefficient of -1, and a 50 ohm load to show the match load. And that is exactly what we see. So now we know for sure that our VNA is calibrated. And just as another consistency check, I've also plotted the through insertion loss. So when we have a through, we expect 100% transmission. So we want to see it as 0 dB here on the plot. And that is exactly what we see. Also, I have plotted something called the noise floor. Now, this is interesting. So this is the open insertion loss. So ideally, when both the ends of the VNA are left open, we do not expect any transmission to happen. And so we expect on the dB plot, we expect the transmission coefficient to be a really high magnitude negative value. Now, this value that you see here can be used to calculate the lowest impedance that this SDR VNA can measure. And we are going to do that later in this presentation.
So basically, we don't connect the cables together, but we still see some kind of measurement And
Yes,
it
and
means
that is
we
called the
can't...
noise floor.
Yeah. Okay.
And we'll use that noise floor because that is also the lowest impedance that this SDR VNA can measure. And being a low cost VNA, we definitely want to understand its limitations and its capabilities.
Okay.
So once we actually do the calibration and we have these consistency checks to understand whether the device is actually calibrated or no, now we are confident in the 2-port method. We know that our device is calibrated. So let's actually move on to the test setup and measure something as simple as a 0.1 ohm resistor.
Okay.
So this is how our test structure setup is going to look. This is our device under test. So as you can see, it's a 0.1 ohm resistor on the breakout board. If I want to show you that here, this is the board that we have. So it has many resistors onto it. And this resistor here is the one that we are planning to measure now. It's a 0.1 ohm resistor. And to do that, what I'll do is I'll connect it to the both ports of the VNA, to the 2 ports of the VNA. Now that we have our setup done, we'll go to the application and we'll click on, we can either go to measure or we can directly take a sweep. So before we actually take the sweep, now is the question, Robert, what do you expect?
So it's
it to look
0.1
like?
ohm resistor, yeah?
Yes.
So I would expect for lower frequencies 0.1 ohm impedance, and then
Okay.
for higher frequencies there will be some kind of influence of the inductance of the lead or something like this. I don't know.
Oh wow, perfect, perfect. You're good. You're good. So let's try and actually take the measurement. So here on the Smith chart, it's plotting the reflection coefficient, but what we are actually interested in is the insertion loss, because we are going to use the insertion loss because we are going to use the 2-point method, and we are going to use the insertion loss to calculate the impedance. And now it's taking the sweep, and let's see if we get what you expect. So as you said, for the lower frequencies, yes, it's giving us a constant kind of output. And now let's see what happens at some of the higher frequencies. It does rise with frequency. You got it correct. So we now have something that we expected, and that's a really good consistency check. So the next step that we do is we go to file and we export the data. So because it's a 2-port measurement, this is a S2P file that we have, and we export that file in the magnitude phase format, and we can save it wherever we want. And then we can pull that file in a free software that we are going to use. It's called Qucs. We're going to use that software to plot the measured data as well as simulate or hack the data.
Okay, but here still, still even here we should be able to, I don't know, can we see the numbers on the low, on the X?
So this that you see here is not the impedance plotted. This is the
Oh,
insertion loss plotted. But
that's
the
why we would
insertion
like to
loss,
import it to the different software, because then we can
yes,
see more
yes.
relevant data.
So this
Oh,
is the insertion loss. And as we discussed, let me just, so we are going to use the insertion loss, and we are going to calculate the impedance using this insertion
oh,
loss.
so basically we only created the tombstone file, or how is it called? S parameter
Yes,
model.
touchstone file. Yes. So we have the S parameters, we have the touchstone file, and we'll import the touchstone file in Qucs, and then we'll plot the measured data, and then we'll actually simulate a RL model for this resistor to understand the actual resistance and ESL values for that a real component.
So again,
let's see how we can do that.
For everyone who actually doesn't know exactly what we are talking about, so basically what we did, we created a model of the physical connection, and then we can import this model. Normally, even for very complex simulations of your PCBs, you create these kind of models. They are called S-parameter models, which can describe, for example, connections on your PCB, and then you can use these models in simulations. Correct, yeah? Okay.
Yes. So moving ahead, this is the model that we build in Qucs to plot the touchstone file that we extracted from this software, from this measurement setup. And to learn how to use Qucs, we did a short, our research group, we did a short presentation in DesignCon. So one of my seniors who is a PhD candidate here in a research group at CU Boulder under Professor Eric Bogatin and Professor Melinda Pickett-May, his name is Aditya Rao. So he did this short presentation at DesignCon on how to use Qucs to import touchstone files and some other basics. It's available on Professor Bogatin's publications page. I'll just share that here. So if we go to Professor Eric Bogatin's professional publications, so if you want, I'll go through it. So Eric Bogatin, CU Boulder. If I go here and then go to Professor Bogatin's page in publications, in professional publications, and then in the DesignCon bootcamp slides, and go to bootcamp presentations, I'll see this set of presentation slides that we did during DesignCon. And the part that my senior Aditya Rao presented includes how to use Qucs for some. So yes, so this is his presentation, DesignCon 2024 bootcamp, Aditya Rao. And this is the agenda of his presentation here.
So basically, following this presentation, you will be, or anyone will be able to import the files.
You'll be able to import the file.
So it's not
also
simple like go to file, import, but you need to do some adjustments or something.
It is really simple. So it is the file import thing, but first you have to build this model. So you are just terminating the SNP block with 50 ohm terminations, and then you double click on this file thing and you import the actual file from wherever you have saved it. And then you have these equations to actually calculate the impedance from the insertion loss. So if you can see, the S11 is the reflection coefficient or reflection or the reflection coefficient, and the S21 here is the transmission coefficient. And from that, the transmission coefficient, we are using the formula 25 into transmission coefficient divided by 1 minus transmission coefficient, the same formula that we mentioned here. So we are just having this equation thing here to plot the impedance or to measure the impedance. But the presentation will give you more insights, as in what are the best practices to use the software and to do this. So if anybody wants to review that, they can go through it. I'll share the link with you as well.
Okay, but I have a question then. Basically, still the software itself, the one which we used to sweep through, can you open it?
Yes.
So this one, it is still useful even with this kind of relative numbers, no? Because if we do this on our own board, we will at least see if there are some resonances or maybe critical places for some specific frequencies.
So this software will show you the transmission coefficient and the reflection coefficient on the Smith chart. If you want to analyze your data the way you want, I would suggest exporting the touchstone file and being able to play around with it in any of the softwares that you want to use.
And you still have to use the same equation, what you mentioned?
calculate the impedance, yes, that's the same equation.
Okay.
So be it any software, maybe the software will have its own syntax or some best practice to write down the some functions, but yes, the equation still stays the same.
Yeah, but basically the shape of the of this graph should be still kind of the same. Just when we go through the equation, we just get the real numbers.
Yes, the shape should be same. And why? Because if you see the equation here, so if you see the equation is 25 times something that plays around with S21. And so we are just playing with some algebraic expressions here, but the shape that we get is more or less the same.
Yeah, okay, let's continue. So
yes, so the first thing that we did was plot the measured data, and it is exactly what we expected. So let's just look at the plot. So the plot that is shown in red is the measured impedance profile, and the plot that is shown in blue is the simulated impedance profile. Now, what does simulated or hacked impedance profile mean? So now when we have the measured data, we need to find out the exact values of the resistance and the ESL, which is the equivalent series inductance of that real resistor component. And to get those values, what we do is we simulate the measured data or hack the data. And what is meant by hacking is we model a R and L circuit, which looks like this in Qucs. And because a real resistor component can be looked at as a resistor having some inductance to it. And so we model this and we use the R, the resistance, and the ESL value as variable. And then based on an intuition, we'll change the values for that R and L. So the R value we know has to be somewhere around 0.1 ohms. And as this component is a surface mount component, usually its ESL value is going to be somewhere around 0.5 to maybe 2 nanohenries at the most. And so that is the kind of range that we can expect. And we can vary the R and L values such that we have an exact overlap between the measured and the simulated plot.
And this can be useful if you have more complex system built from these same components, then you can basically simulate it.
Yes, yes. So when we have this exact overlap now between the measured and the simulated data, that's when the values of R and L that we have here are the resistance and ESL values of this real resistor component. And so when we do that, we say we have hacked the model. And so this is called measurement and simulation correlation. So the first thing that we understand from this is the value for the resistance that we arrived from this two-port measurement method is exactly 0.1 ohms. And that is what we expected. And the ESL value of this component, this real resistor, is 1.37 nanohenries. And that is also something that we had expected because this is a surface mount component. So the first thing that we understand is we get a really good correlation between the measured value and the simulated value using this simple first order RL model. So we are focusing here on low cost tools, free softwares, and simplistic things to get a good view, to understand a view of the components that we are going to use in the PDN or analyze them. So the simple first order RL model is giving us a really good correlation between the measured and the simulated impedance. And this, we also understand that this real resistor component can be modeled as a simple RL circuit. And we also have confirmed that the resistance, what we expected as a result of the DC measurement, we have the same resistance. So we now have confidence in this two-port measurement method, and the ESL value for this SMT component is also something that we expected in the range that we expected. So now that we are able to measure something using this two-port technique, let's try to measure some more resistors and see what pattern do we get.
But again, before we continue, I would like to point out, so basically this means with this cheap device, we should be able to measure impedance around 0.1 ohm with no problems and get like relevant results.
Absolutely no problem. Yes. And so now that we know, we can go ahead and measure some more resistors, and let's see what we get out of
To
them.
have some fun.
Yes. So now we have a 1 ohm resistor, a 0.5 ohm resistor, a 0 ohm jumper, and I also have a shorting trace. So the shorting trace is just a short. Instead of the component, we just have a short on the PCB. That's the shorting trace. And I compare all of them with, I also have the 0.1 ohm that we measured earlier. So I followed the same test setup that I just showed you a couple of minutes ago. I imported the touchstone files that I got as a result of the measurement in Qucs. I hacked the data or simulated the data as we saw earlier, and then I've plotted all of them on this plot. So one thing that we see is at the lower frequencies, I see a really nice gradient of different resistors having different impedances. But as we go ahead in the frequency range, I see all of the plots merging into a single plot. And did we expect that? Why is this happening?
Because I don't know, they have same footprint, I don't know.
Exactly. So I have mentioned it here, but yes. So all of them are 1206 components, and all of them have the same footprint. And that is why at lower frequencies, when the resistance dominates the impedance, we see that all of them have different resistances. And that's why we see a gradient in the resistors. And then as we move towards higher frequencies, the inductance dominates the impedance. And that is why we see that all of the plots have the same ESL value. And that is why they have the same kind of impedance.
What
And
about
so
the
to
shorting
double,
trace? Why it's also
yes,
the same?
because it also has the same kind
Length.
of length as because we are just shorting these two pads between the two shorting the two pads where the resistor was placed, so it has the same dimensions. So that is
Okay.
why we see the same ESL value, and that is why we see the same impedance, because the ESL value dominates the impedance at higher frequencies. And if we want to double check whether our intuition is correct, let's check what values we got when we hacked this measured data. So the values that we got are giving us really good insights. So the 1 ohm gave us a value of 0.99 ohms. The 0.5 gave us a value of 0.49. The 1 ohm, which we measured earlier, gave us this value. And this is one interesting fact that I would like to tell everybody. So everybody knows that the 0 ohm jumper is not actually a 0 ohm resistor. It should have some resistance to it. But now we exactly know what the resistance of a 0 ohm jumper is, and it's in the 20 milliohm range. And the shorting trace has a resistance of 4 milliohms, and that's really low. So during our last measurement, you were talking about measuring impedances in the 0.1 ohm range comfortably. See, we have measured something that's as low as 4 milliohm.
But do we know it's really correct?
Yes, it is, because now we have, so that is why I did the 4-point Kelvin DC measurement.
So you did the 4-point Kelvin measurement also with this shorting trace, and it was also 0.004?
No, I did not do this for the shorting trace, but I did it for these resistors. I did it for these 3 resistors. And now it is good enough to establish confidence in the method that, okay, this is what we expected out of as a result of the DC 4-point Kelvin measurement. And we got all those 3 measurements within the same tolerance that we expected using the 2-port method. And this gives us enough confidence in the method. So now when I have enough confidence in the method and I'm using the test setups, I have my calibrated equipment, I can be rest assured that, okay, the measurement values that I'm getting out of it are good. So that is also something that I expected, right? So I expected the 0 ohm jumper to have a resistance that's lower than the actual 0.1 ohm resistor, and then a shorting trace to have a resistance further down on the resistor profile.
And
if we check,
so
yeah, sorry,
is
go
not
ahead.
the noise floor going to influence this measurement for very low impedance?
Exactly. It is going to do that for measurements that are lower than the noise floor. And that is why we will measure what the lowest impedance this SDR VNA can measure.
Okay.
So the second thing that we get out of this measurement is, if you look at the hacked model, all of them do have the same ESL value. And our logic behind why the plots are merging into the same plot was correct, because now we have verified that all of them have the same ESL value and hence the same impedance at higher frequencies as the ESL value dominates the impedance. So we have a really nice takeaway from this measurement, and that is that the footprint of a component, it plays an important role in determining the impedance at higher frequencies due to the ESL.
I would like to ask why this measured impedance graph very close to DC has all these points around the there.
Yes, so that's a good question. So as we discussed, we are going closer and closer to the noise floor, because as we are going, so we are going closer and closer to the noise floor, and then you will see some when we move to the next slide, next set of measurements, you will see what I'm talking about here.
Okay. Oh yeah,
Yes.
I see it now. Because the noise floor is a little bit higher for the lower frequencies.
Yes. So the thing is, now that we have measured something that is as low as 4 milliohms, and we shouldn't forget that we are using a really low cost device here. So now it's the time to check how low on the impedance profile can we get. So this is something, this question has been bugging you since the start of this presentation, because we have been doing something low cost, and when it comes to low cost, we should also know the limitations of the device. So now we'll try to model something that has a really low impedance, so a really low R and L value. And so I tried modeling a solder joint or a solder blob that is really wide and thick, so that it will have really low R and L. And let's try and compare this solder joint that we modeled along with the noise floor, which is the lowest impedance that this SDR VNA can measure.
Okay.
And when we do that,
so we are going to measure the short, as good short as you could make.
We are going to measure the open. The isolation is the noise floor.
But the blob is doing the short, no?
Oh yes. The blob is one measurement. So I have 4 measurements here. The first one is the 0 ohm jumper that we have in the earlier slide.
Yeah, I
then
meant
I
blob.
also have the shorting trace. Yeah. I also had the shorting trace. I also have the shorting trace, and these 2 measurements are the same as we did in the earlier slide, but I have them just to give our audience an idea as to how low on the impedance profile we are getting.
I understand now.
And then we have, and then we have these measurements of the solder blob and the noise floor. So this is the solder blob test structure that we have. So it's really wide and thick to have low resistance and ESL value. And this is again the RLN model that we use to hack or simulate the data for the noise floor. And once we do that, what we understand is, let's look at the results that we have. Wow. So the solder blob that we have has a resistance of 0.55 milliohms. And the noise floor is even less. It's 0.15 milliohms, and that's really less. And if we check the ESL values for these, the noise floor is 0.25 picohenry. So just imagine a $450 VNA can get us measurements, such low measurements on the impedance profile. So a resistance of 0.15 milliohms and a ESL value of 0.25 picohenries. And that's really good for a $450 VNA.
Who is the manufacturer of the VNA?
So
can we open website? I'm curious.
Sure. So if
and you know what is also interesting in this, when you measure this blob, we can actually now see that the inductance is lower, as I would expect.
Exactly. So the resistance is also lower. We can see that here, and the inductance is also lower as compared to these.
That's what I mean.
We have made it thick and wide, and that's exactly what we wanted to do.
Yeah. So can we find it on website? I'm curious.
I can show it too. I had the. I can search it. So it's called an SDR VNA. This is it. SDR Kits. That's their website, and this is the model that we are talking about. They have some latest models as well.
So who is the manufacturer? Where is it manufactured? Who developed this? Is there about company something? If you go down, yeah. About us. What is about us?
Should I go to contact information? Maybe it will
Try.
have their.
What is that? I'm just curious, you know.
It's UK.
United Kingdom. Okay. Okay, we can go back to the presentation.
Yeah, perfect. So now that we have established the two-port method as a reliable method, and we also have measured simple test structures like a resistor and some different resistors, and we also know the limitation of this device as to how low on the impedance profile we can go. Now we will measure something that is a little bit complex, which is a capacitor.
Okay.
So here we are going to use a 15 microfarad MLCC surface mount capacitor. And this is the test structure, and this is our board that we are going to plug in between the two ports of the VNA. This is the model again that we'll use in Qucs to plot the measured data, the touchstone files, and calculate the impedance of the device under test. So do you want me to take the actual measurement again for the capacitor?
No, we don't have to do that.
Okay.
I think it would be exactly same as what you did.
Exactly the same.
Resistor.
So I just place this and then run the same button.
Yeah. Okay, so what are the results?
Okay, so before we actually move on to the plot, I'll ask you again, rule number 9, what do we expect as a result to the measurement of the impedance plot?
Classic capacitor stuff.
Perfect. So let's actually, without wasting any time, move to the measured and the simulated data plot. So the plot in the red shows us the measured data, and this is exactly what we expected. So at the lower frequencies, the capacitive behavior of the capacitor will dominate the impedance. And after the resonant frequency here, the inductive behavior will start dominating the impedance. And that's why we'll see the graph moving upwards kind of linearly. So this is the measured data in red that we have. And then we have used a simple first order RLC model to hack the data as we discussed earlier. And when we actually hack the data, we get a fairly decent correlation between the measured and the simulated data. So let's look at the values that we get for the ESR or the equivalent series resistance, the ESL equivalent series inductance, and the capacitance. So the capacitance value that we have here is 13.2 microfarad. The capacitor was rated to 15 microfarad. But the first thing is that we have confidence in this technique now. And also these capacitors that we have are rated to plus or minus 20%. And this value is well within the tolerance. So whatever we have got as a result to the measurement, it's accurate. And then again, this being a surface mount component, we expect its ESL value to be low, somewhere from the 0.5 to maybe nanohenry range, and we get that, and that is what we expected. And the ESR value for this MLCC capacitor, we get it as 3.6 milliohms, and that is also the kind of range that we can expect for MLCC capacitors. One thing that I would like to point out here is that we see that while trying to get a really good correlation between the measured and the simulated data, we see a short discrepancy here, a small discrepancy.
It was my next question. Can we
I
fix
know
it?
how I've seen your videos now, Robert. I know what you're going to ask next. So yes, so we see that we have this small discrepancy in the measurement simulation correlation. And so we also know that for such low inductances for a capacitor, this is the best kind of correlation that we can get using a first order RLC model. So if we have to get a better match than this, we should move to second order models. But that's not the point of this presentation. Here we are just seeing how to measure and analyze the low impedances of these small components. So a first order RLC circuit is good enough, which gives us this measurement and simulation correlation.
Yeah, I guess even if we just take different physical components, this may maybe move a little bit because of the tolerance. So it's not maybe so important to have like exact model of this specific capacitor.
Because everything that we are doing here all the components, the resistors, the capacitors that we have, all of the things are low cost, and they are bound to have some tolerance. So as long as we are getting our values, and as long as we have established confidence in the method first, and then we are getting values that are well within the tolerance range, I think it's that is good for the analysis.
Okay. Okay. What do you have on next slide?
Yes.
Fun
So
stuff.
now that we are, yes, interesting stuff. So now that we have measured a capacitor and plotted its impedance profile and analyzed it, let's move to another factor which will affect the impedance at higher frequencies. So we already saw how the footprint affected the ESL value and in turn affected the impedance at higher frequencies. We're going to look at another factor now. So we have, let me explain the structures first. So we have 4 different structures. All of them are 0.22 microfarad MLCC capacitors, surface mount. And the only difference in the structures is the way in which they are mounted on the planes. So the first structure has 2 vias, each via 20 mils from the pad. Then we move the vias closer. So now we have 2 vias, each via 5 mils from the pad. Then in the third structure, oh, we don't see the vias. So we have 2 vias, each via right below the pad. And then we have the multiple via structure, wherein we have 6 vias in all, 3 vias near each pad. And now what we are going to do is we are going to compare the impedance profile for all of these 4 things, and let's see what we analyze out of them. So we can see that the impedance profile for the lower frequencies, they all overlap each other. And we expected that to happen because at lower frequencies, the capacitive behavior dominates the impedance, and all of the 4 capacitors have the same capacitance value.
Yeah, the
And so
via
we
connection
expected
is not important for the lower frequencies because vias are the
yes.
elements and the connection is the element which will bring the inductance, not the capacitance.
Yes, yes. And as we move at higher frequencies, the position of the vias, it affects the ESL value, which dominates the impedance, and that's why we see all the plots giving us a nice gradient. Now, with our intuition, before looking at the legends and before looking at the colors on the plots, let's use our intuition to predict what which of the structures should have the highest ESL value and highest impedance at higher frequencies, and which one should have the lowest inductance. So when we have the vias really far apart, the loop that it is forming is big, and that's why we expect it to have a higher inductance and higher ESL value. So it should give us a high impedance, highest impedance on the impedance profile at higher frequencies. But when we move the vias closer, we kind of reduce or shorten the inductive loop, and that's why we expect a smaller ESL value. And then when we move the vias inside the pad or below the pad, we have a much lower ESL value and impedance. And then when we have multiple vias, we have the least ESL value and least impedance. Let's check whether we have that. So the one in red is vias when vias are far apart, and yes, that's the one that has the highest ESL value and impedance at higher frequencies. And we see this gradient, and the one with multiple vias has the lowest impedance and ESL as we expected. Also, to verify this, we have simulated the data, and we have the data for the ESL values of all these structures. And yes, that's exactly what we expected. So when the vias are far away from the pad, we have an ESL value of 4.05 nanohenries, which comes down to about 1.225 nanohenries for the multiple via structure. So now we know if we have to reduce the impedance of a PDN, and if we have we have choice of different via positions, the multiple via position is the one to go ahead with to have lower ESL value and lower impedance at higher frequencies.
What I would like to point out is for power delivery, we may not be really interested go up to, I don't know, 1 gigahertz or something, because 1 gigahertz will never go through the pads and the bond wires and everything. Only the frequencies, maybe, I think most people say like up to 300 megahertz, maybe that's what we are interested about to investigate the path on our PCB. I'm talking about PCB, not about power delivery up to the chip. Yeah, only on our PCB. So I wanted to highlight this. I don't know if it's exactly 300 megahertz, but that's what I mostly heard. And I wanted to point out this because I would like people to understand that we are not looking for power delivery up to I don't know gigahertz, because for standard chips, maybe for some special boards you need to, but for like standard chips the limitations will be in the packaging, I think. Correct? I don't know. Okay, so let's go ahead. I wanted to mention this.
Yes, perfect. So now that we know among the different via positions that we have, multiple vias positions gives us the least ESL value and least impedance at higher frequencies. So what do we do if we have to reduce the impedance at higher frequencies further? Because we have already looked at the different via positions now. So what do we do?
I think the best connection is to connect everything on top layer, but I don't know if you have simulations for this.
I'm guiding you to a different type of capacitor here. So what we're going to try and do is use an X2Y capacitor and try and check if that gives us a lower ESL value and lower impedance at higher frequencies.
Okay, let's have a look.
Let's do that. So what I have here is the multiple via structure and the X2Y capacitor. And why do I have the multiple via structure? Because that gave us the lowest
reference.
Yes, to compare it with the X2Y capacitor, because that was the structure that gave us the lowest impedance at higher frequencies. And when we compare it with an X2Y capacitor, we see that the X2Y capacitor gives us a lower ESL value and impedance at higher frequencies. Now, just a note, both the capacitors that we have, the X2Y capacitor and the capacitor that we used earlier in the MLCC capacitor, both have different capacitances. So these two plots show us that, okay, the capacitor values for both of them, the capacitance values for both of them vary, but that is not what we are interested to look at in this slide. So in here, what we are interested is in the ESL values, and we can clearly see that the X2Y capacitor has almost half the ESL value as compared to the multiple via structure. And why is that? So an X2Y capacitor is a 4-terminal capacitor, and just to visualize it, we can imagine that to be like 4 capacitors in parallel. So when we have 4 capacitors, the inductance or the ESL value of the capacitors will be 1/4 of the values, and that is how it has a lower ESL value. So a good option, so if we have exhausted all the ways in which we can have via positions, and we want to further reduce the ESL value, what we can do is, instead of having 2 MLCC capacitors with multiple via structures, we can have one X2Y capacitor. So this helps us reduce the real estate on the board or the PCB, because instead of 2 capacitors, now we just have one X2Y. But it comes with a cost. So the cost of an X2Y capacitor is more than the cost of normal MLCCs, and it's always going to be a trade-off. But yeah, this is some option that we can always explore.
It's interesting to know.
Yes, it is very interesting to know.
So and I see next slide is probably like standard capacitors.
Yes. So now we have discussed 2 things. So the first one with resistors was how the footprint affects the ESL and impedance at higher frequencies. The second thing that we learned was how the via positions affected the ESL and the impedance at higher frequencies. And now we are going to look at one more factor. So this presentation is majorly about the 2-port measurement method using the low-cost VNA, but I also wanted our audience to walk away with some principles that would help them maybe design or analyze PDNs later.
This is very important to see, because this will show everyone differences between different components. It's not like 10 microfarad capacitor for everything. There are differences between different kind of 10 microfarad capacitors.
Yes, yes. So moving on to the next part. In this part, we have compared an electrolytic capacitor, a tantalum capacitor, impedance profile, with the SMT MLCC capacitor that we measured earlier. So as a remark, I would like to mention that all these three capacitors have different capacitance values. And by now we know that, okay, the capacitance dominates the lower frequencies, and we can see that here. So all three of them have different capacitor values. And we can also reconfirm that from the values that we got as a result of our measurement. So all these three have different capacitance values. But what we are really interested in here is something else. So the capacitors, electrolytic capacitor and the tantalum capacitor that we have in this case are leaded capacitors. So the structure is a leaded structure, and the SMT-MLCC that we had is a surface mount structure.
It's the reference what we did before.
Yes. Sorry?
It's basically the one what we did before for our reference to see where.
Yes, exactly. So what we are interested is in looking at frequencies, or in looking at impedance at higher frequencies, which is dominated by the ESL. So what do we expect the ESL value to be for a capacitor which has long leads? So for a capacitor with long leads, we get that inductive loop, and with that inductive loop, we have an ESL value that is much higher as compared to an SMT component. And so is that what we get as a result of the measured and the simulated value? Let's see the values for the ESL. Oh yes, the value for ESL for the SMT capacitor is about 0.75 nanohenries. And if we compare that with the electrolytic and the tantalum capacitor, which have leaded structures, it is 8.4 and 7.7 nanohenries. It's almost 10 times the value. And this is exactly what we expected because of the inductive loop that the leads are forming here. And we can also see that both of them are leaded capacitors, and their ESL values are in the comparable range. So yes, this tells us, this consistency check tells us that, okay, we expected the correct thing and we observed what we expected. So this establishes much more confidence in the measurement technique, and also tells us that the structure of a component is important, and we need to have more SMT components, or components which do not have the inductive loop, which will induce that ESL value which dominates the impedance at higher frequencies. So in order to have a lower impedance at higher frequencies, we need to choose SMT components over these leaded structures.
Yeah.
So that's another takeaway that we can have.
Yeah, basically I would like to translate what you just said. Like when we have a look on this electrolytic capacitor, we can see the ESR, lowest ESR around, I don't know, 1 megahertz is like, what, 3 ohms or something like that. So it would never be able to kind of help us to deliver current which need maybe impedance to have around 0.5 ohm. We really need like special capacitors for this, correct?
Okay. When you were referring to the MLCC, you said
to the electrolytic capacitor.
Oh, you are referring to the electrolytic.
Yeah,
Okay,
because
perfect.
Because if it has the ESR like 3 ohms, then it can never deliver power for high currents, because these high currents, they will be not able to flow through these 3 ohms.
Okay, and then one more thing that you must have noticed here is for the electrolytic and the tantalum capacitor, the first order RLC model that we used was not giving us a really good correlation in this region. And this is another thing that tells us that, okay, for capacitors, and especially for electrolytic capacitors and tantalum capacitors, if we want a really good measurement simulation correlation in these regions, we will need to use second order models. But in our case, this was not the region that we really wanted to analyze. So a first order model is good enough for our analysis.
Mm-hmm. So what is next? What would you recommend? I think this is like, is it end or what is it?
So this is just the takeaway slide.
Yeah. So what would you recommend if, what would be the next steps for people after they watch this video? What can be very helpful for them? Like once they know how to...
Do you want me to go through the takeaways first or answer this?
We will go through takeaway a little bit later. So basically, they could play with these standard components. They could maybe measure the components what they use and then create perfect models for the simulations. Or in the next step, they could maybe measure their own boards, the impedance on the boards, and or what would be the next step? What would you recommend?
So the next step I would recommend is to move to measuring something like the impedance profile for the PDN of a maybe microcontroller or something. The first thing that they will need to do is a lot of reading. And because actually building a microcontroller and being able to measure the impedance profile of the microcontroller using a VNA, that's not the hardest part. It's really easy to design a microcontroller like an Arduino and maybe take the measurements for the impedance profile. But what we need to learn from here is that we now know the measurement setup. We now know how to extract the data and hack the data on a preliminary level. But the analysis part of the data is the most important part. When we measure the impedance profile of a microcontroller or something that is more complex, we'll see a lot of signatures in the impedance profile. And we should be able to understand why we are getting all those signatures.
Signature,
So
you mean
between
peak and deep, yeah?
Yes. So, and those signatures we are going to get as attributes to some features that are there in the design of that particular device. So to understand that, now we have understood just resistors and some ways of via positions and maybe some types of capacitors and some other areas here and there regarding signal integrity. But we have to do, our audience, me, everybody has to do a lot of reading to understand all such different aspects so that when we actually build something like a microcontroller and we are able to measure the impedance profile across the operating frequency range, we should be able to analyze why we are getting each of those signatures, and only then we will be able to make the impedance profile better. Or if we see maybe some some peaks in the impedance profile that go beyond the target impedance, and we want to reduce the impedance at those frequencies below the target impedance, we should be able to first understand why we are getting those peaks at those particular frequencies. And to do that, I would suggest reading about power delivery networks is the best way to go ahead.
But they still can measure it. I've done a video on similar topic. We did measure it on the power pin of microcontroller. We use different device for this, but if anyone would like to see, they can watch the video. And it was super interesting video, one of the really best videos what I ever done, because we actually could see the noise on power supply for specific frequency, which we actually find out based on this PDN impedance. We knew at this frequency there will be problem, and there really was a problem. So it's like very cool video.
Wow.
Okay, we can go through the last slide.
Perfect. So let's just summarize what we did in this presentation. So we talked about the two-port method using this low-cost SDR VNA, which can eliminate the artifacts associated with contact impedances. And we measured different test structures. We measured the low impedances of these test structures over the frequency range of 1 kilohertz to 1.3 gigahertz. And we established that the two-port method is a really low-cost method because the VNA that we used is a $450 VNA and also a reliable method for low impedance measurement. Then we used simple RLC first-order models to be able to simulate or hack the measured data to understand the RLC characteristics or values of these real components. And we got a really good measurement and simulation correlation using the first-order models. We also, being a low-cost VNA, we also found out the limitation on how low on the impedance profile we can measure using this SDR VNA. And we had some key takeaways, which we learned that, okay, the footprint, the type of the structure, whether it's leaded or whether it's surface mount, and the way we have the via positions, it matters a lot in determining the ESL for those components, the equivalent series inductance for those components, which dominates the impedance at higher frequencies. So that is all for today.
No, I have two questions. I still have two questions. So first one is, what about probes? If we go on the website of this VNA, do they sell also probes? Because if we would like to measure our board, we need kind of special probes for this, no?
So the probes that I have used, they come with the VNA.
But you only use cables and you need to use the
Yeah.
special connectors for your test setup. But
Oh,
if you would like to measure real board,
you mean the UFL connectors,
yeah.
connecting to pigtails.
Yeah, but if you would like to measure your board, you need some kind of probes.
Yes, so a good idea to measure your board, the PCB, is to have UFL connectors on your PCB and then connect them through pigtails to the VNA cables.
And my second question is, so what do you do? What's your job?
So just to introduce myself, my name is Adinath Phene. I am a second year graduate student in the high-speed digital engineering program at University of Colorado under Professor Melinda Pickett-May and Professor Eric Bogatin. So I completed my undergrad back in India in 2019, and I joined the Signal Integrity program here at CU Boulder last year. Currently, I am interning at ANSYS, and I'm also working under Professor Eric Bogatin for his research projects.
Cool, cool. How do you like it in ANSYS?
Oh, it's really good. So I really like the education that I'm getting here, and to be able to work under Professor Eric Bogatin and Professor Melinda Pickett-May's guidance, it's really good. So I've learned a lot of things, and I also presented at DesignCon 2024 this year along with Professor Eric Bogatin, and that was also a really good experience. And that is the place where we met. So
yeah.
that is the reason why this video is happening.
Thank you very much, Adinath, for say, I would like to thank you for your time and for preparing all these slides, because I've done some simulations, especially on via placement around capacitors, and I was curious if someone really measured the differences. You did it, so it was interesting to actually see you can really measure some difference for what the difference which is between different connections of different of the same capacitor. So it was like super interesting to see actually real measurement. So thank you very much, Adinath, for preparing all these.
Thank you so much, Robert, for having me on the video. Thank you so much.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.